All right, this is a polar coordinate graph. We're drawing this function, and this is what we have so far after we plotted some points. So we've only gone up to pi over 2. All right, what do you think is going to happen when we go a little bit farther? So what are good halfway marks over here? 5 pi over 4 looks like. 3 pi over 2. And 7 pi over 4. Until we get to 2 pi. So you think it'll draw it on the other side? Let's take a look. So let's start over here at 5 pi over 4. So at 5 pi over 4, what's sine of 5 pi over 4? Something with a root 2 over 2, except what? Negative. So it'd be negative root 2 over 2. Now root 2 over 2 is about 0.7, right? So where am I going to draw my dot if I was plotting points? Am I going to draw it down here in the third quadrant? Where am I going to draw it? In the first quadrant? Do you guys understand why? The negative part of that, right? This is r in the positive direction. This is r in the negative direction. So in the negative part of that is where you're going to draw your negative 0.7. Okay? Maybe I didn't do that line correctly. So that's the negative direction. So where should I put my point? What? It's already there, right? I would put my point where this point is. It's already here. So what does it look like it's doing? It's retracing the exact same circle that we drew already. So when this is at 3 pi over 2, when this is at 3 pi over 2, it's pointing down, it's going negative 1. So that's directly that point over here. And then negative root 2 over 2 again. And then here, it goes back to 0. So by the time you get back to 2 pi, you're back to where you started from. Yeah? Yes. Yeah, so when your r values are negative, it's going in the opposite side of which the arrow was pointing. Does that make sense? So really, you could draw this out if you just go from 0 to pi. Where's pi? Oh, I didn't put pi. Let's put pi. You can draw this out from 0 to pi and then be done with it. And if you go from 0 to 2 pi, you're actually drawing it twice. And that could be an issue when you're following a particular path. It's important to know if the path is drawing this thing once or twice or more than that. Okay? So, visual might be your calculators. Remember your calculators? I don't know if the TI-89 people were able to figure out how to do parametric equations, but I'll show you how to do polar equations with this and then see the drawing. So the first thing we need to do is we have to make sure that we are in polar coordinate functions. So with the TI-83 or 84, I would click on mode. And where it was FUNC, which is the regular function that we've graphed before, and PAR for parametric. There's the next one's POL, which stands for polar. So you can select that. That should be your first step. And then if you press Y equals, you should see that now you have an R list instead of a Y list or an XT, YT list. Now you have an R list, a list of possible R values. We did the sine function by hand. Let's take a look at what the cosine function is going to look like. So I would select cosine, and then this button that says xt theta n, it knows which function you're dealing with. So if you press that button, it's not going to give you an x like it would for a regular function. It's not going to give you a t like it did last time we used it. It's going to give you a theta because it knows that it's in polar coordinates or polar graphing. Okay? All right, the next step would be to adjust your window. If you look at the window, it's a little bit different from last time also. It's going to ask you for a theta min, a theta max. That's the value over there that Moises was filling out from 0 to 2 pi. Let's go from 0 to 2 pi because that's usually the standard way to approach things, and we'll see when we draw this that it's going to go twice. 0, enter, and then 2 pi. Let's go ahead and press 2 and then find your pi. Or you can just say 6.28 or something. The theta step, I didn't mess around with the t step. I'll mess around with the theta step in a minute, but let's say the theta step right now is 0.13 it says. That's like the default. And then I want to be able to capture what I need to capture. I think the window that we had last time from negative 1.5 to 1.5 would work. So I think that's still the same for the x min and x max, y min and y max. Now if I just graph it, it's just going to give you the image. So I don't know if that's going to be enough for us. So after I take a screenshot of this and put it in our notes, I'm going to adjust the window again. I'm sorry, not the window. I'm going to go back to this this page again, the y equals. And then the same options on the all the way, if you go all the way on the left, if you press enter maybe a couple of times, it'll actually draw it out for you so we can see the drawing. All right, so I have this little dot with this little thing. So if I hit graph, you can see that it's drawing it, and it's drawing it twice. You can also see it doesn't look like a circle, but you have to adjust the window accordingly. I think there's a way to zoom. Zoom box, maybe? Because the window screen is stretched out, so whenever you try to draw a circle, it looks like an ellipse. But let's see if zoom box would work. Oh, square. Okay, let's see if zoom square would work. That looks more like a circle. All right, so if you go ahead and adjust, if you go back to the window and adjust this, instead of going from 0 to 2 pi, let's say we just go from 0 to pi, 3.14, and then graph that, you see that this is only going to draw at one time, and then that's all you need to draw that circle. Okay? Now if we want to do something weird, remember that step that I was talking about? Calculators really just draw straight lines. And if you put these points close enough together, it looks like it'll eventually curve. But if you take my steps here and take steps of bigger steps like 0.5, that's a little ridiculous. And let's go to 2 pi again. What's 2 pi? 6.28? And then you graph that. It's not as smooth looking, right? Because it's drawing these things in as lines. In fact, instead of going to 0.5, let's actually be ridiculous. 0.7, 0.8. Now, it doesn't even look like a circle, right? They're just putting sample points and then drawing straight lines between those sample points. So if you make those sample points big, with a big gap in between, you're going to see more lines than you need to, and then you should. Okay, but if you make those small, instead of 0.8, make it 0.1, then it'll draw a smoother looking graph. It'll take longer because it has more points to plot and more lines to fill in. But it'll be nicer looking. All right. So how did it go again? This is mode. Select POL for polar, and then y equals, and then type your function, and then choose, especially if you want to see how this is being drawn out, then you can choose this, make sure you choose this to an appropriate, the line with a circle on it would actually draw it out. And then your window, small steps, and then your start and your finishing point. Start theta, end theta. And then this would be your screen. So if you plot something, you don't see anything there, you might want to adjust your screen or press some zoom thing so that it would fit. And then this is your graph. All right? So that's how we can visualize. Is it new for people? How many people have seen this before? Polar coordinates. Okay. Some Calc 2 courses go over a little bit of the polar coordinate stuff, and sometimes this is covered in pre-calculus. And so you may have seen it in those places. All right? But what you might have probably not have seen is the calculus that we're going to do with them. So we'll get into the calculus in a minute. But let's actually take a look at so we looked at the graphical point of view. We look at the numerical point of views by plotting some points. We saw how they look like. And now let's take a look at the analytic part, the symbolic algebra part of it. Probably should have started with the objectives in the beginning. All right, I'm not going to go over that. It's just so polar coordinate equations. So polar coordinates makes the relationship between two variables, x and y, with the other two variables, r and theta. And the relationship gives you the algebraic formulas needed to describe polar coordinates. So we rarely see that graph r theta that's on the side of the board over there. We don't usually see that. What we normally see is the graph of x and y, because that's what we're really interested in. But we see how the polar coordinate lives in this Cartesian world. And the polar coordinate lives in the Cartesian world by an angle of theta measured from the positive x-axis and a radial distance of r measured from the origin and so this very point over here that we would normally call xy, because you have an x value and a y value associated with it, can also be considered as r theta, given the angle of inclination of that line segment and the length of that line segment. And then the idea of a negative r would just be pointing in the opposite direction of the ray according to the angle. Now these equations over here all come from this drawing, right? You can draw your right triangle, your angle, and your lengths x and y, and then you can come up with as many equations as you need to. There's 4 equations here. X squared plus y squared is equal to r squared. X is equal to r cosine theta. Y is equal to r sine theta. And then the ratio between the opposite and adjacent sides, the opposite over adjacent, is the tangent of the angle. So it's all there. And if you can just remember this picture, then these equations should come naturally, or should come, or something. And if it doesn't, just memorize these equations, then you're all good. Okay? Any questions? Negative values of r? Yeah. Okay. So there's a few things to do here. I mean, graphing, of course, is important, and sometimes they like to go between polar coordinates and Cartesian coordinates and vice versa, and so that's what these equations are really good for. Is that if you have a circle, for example, how would you translate that to polar coordinates? So that's like the easy problem. So given x squared plus y squared is equal to 1, we know that's a unit circle. How would you translate that into polar coordinates? We already know the answer because this is one of the activities that we did, but x squared plus y squared is r squared according to one of the formulas, is equal to 1, and then you can take it one more step. Square root of that is just 1. So r is equal to 1 is a circle if you were to draw that in polar coordinates. And you can take your calculator and put 1 in for r and then draw it out. And then that's what you'll get. Right? Circle radius 1. So the more interesting problems would be things that aren't just circles and things. Do I have any examples? Let's see. Oh, let's try to graph a few of these things. I just copy the whole. Let me just copy the whole thing on a sheet and see if we can picture what the graph should look like. And if it gets too hard to picture what the graph looks like, we'll ask our calculators to figure it out. R is equal to 2. What's that going to look like? Circle radius 2. That one's easy. Radius 2 or 4? Radius 2. Okay. R is equal to theta. We actually saw that being drawn out, right? That was our first example. How does this look like? Spiral. That was a cool graph. All right, these other ones are going to be considerably more interesting. Let's start with this one. Theta is equal to theta is equal to pi over 3. What do you think that's going to look like? It's a dot? A line? Straight line? Vertical line? So this graph over here says that, what does it say about r? So when you have a graph like y is equal to 2, think about that graph. What's that graph look like? It's a horizontal line, right? Some people say straight line. That's what's a straight line? That's a straight line. The line's straight. A horizontal line. So y is equal to 2 is a horizontal line. There's no x in there. How do you know the graph a horizontal line when there's no x? What does the x missing in that graph mean? X is no value or an infinite number of values? All real numbers? It doesn't matter what x is. Y is always going to be 2. Right? Think about that. Y is equal to 2. There's no x. It doesn't matter what x is. Y is always going to equal to 2. I have theta is equal to pi over 3. There's no r. What did I just say? I just said there's no r. Doesn't matter what r is. Theta is always going to be. So what do you think it's going to look like? Vertical line, horizontal line? Remember, it doesn't matter what r is. R could be 0. Well, I'll just put 0. But if r is equal to 1, what's theta going to be? Pi over 3. Well, pi over 3 is like right here. What if r is equal to negative 1? Theta is going to be pi over 3. What if r is equal to 2? Theta is going to be pi over 3. Right? Doesn't matter what r is. Theta is always going to have an angle of pi over 3. So this is going to be a line with an angle of pi over 3. And if you want to look at it from a different point of view, theta is equal to pi over 3. Let's take a look at some of those equations and see if it'll help us. Theta, oh, there's a tangent theta over here, y over x. Let's see. What was theta again? Pi over 3? So, tangent of pi over 3 is equal to y over x. Let's see. Say y equals, do you know what tangent pi over 3 is, by the way? I'll just put tangent pi over 3. Tangent pi over 3 is just a number. Did anybody figure out what that number is? 1.73. What? Root 3. So this is just a line going through the origin with slope root 3. So the slope of this line must be root 3. Okay? So that's what that is. Okay, so now the rest of them, I want you to do it on your own. Should I do one? I'll do one. Which one? One minus 2 plus 1x. Let's do that one. And I'm just going to use my calculator. No? No, use the calculator? All right, whatever. If I'm not going to use a calculator, I'm going to need a hand. And what I'm going to do is I'm going to draw it with theta and r first to see if I can recover from here. Imagine that activity that you guys were doing where you twist the radial measurement around and see what happens. So 2 cosine, let's see, cosine theta, I think cosine theta looks like this. Now the 2 in front just makes it extend, changes the amplitude, and then the negative makes it go reflect about the y-axis. And then add 1 to it, so move up by 1. Wait, what's going on? So that's what it's going to look like. So essentially, I go from 1 to 3, or negative 1 to positive 3. So how's that going to look like in my actual graph? Let's see. When theta is equal to 0, I'm at negative 1. Theta is equal to 0, I'm pointing this way, but I'm going to go negative 1 on this side. So I'll start over here. And then at pi over 2, I'm going to, it looks like I'm going to go from negative to positive. All right? So as this is turning, let me make this into a line. Make it longer. As this is turning, before I get to pi over 2 is over here because I shifted it up. Before I get to pi over 2, I'm going to cross the origin, and by the time I get to pi over 2, my height is going to be, I think, 1, right? So by the time I get to pi over 2, I'm going to be at 1. Alex? Yeah, so this is 0, but remember, since it's negative 1, I'm going in the opposite direction. So this is my first point right here. And then what's happening is that it'll be negative. It'll be negative, and at some point over here, I'm going to shrink down to 0. So it's going to go over here. And then it's going to be positive. It's going to go until I get to this point 1. So now I keep going this way. By the time I get to pi, I'm going to be in the positive distance of 3. So 1, 2, 3. I'm going to be over here. And so I'm just going to be increasing from pi over 2 to pi. My graph is going to be increasing. So I think that's going to cover this, something that looks like this. Okay? Let's keep going. Over here again, this is 3 pi over 2. It's going to have a height of 1. So by the time I am pointing this way, I'm going to be at 1 again. So 1 is this distance over here. And looking back at the graph, it's going to shrink down to this. So imagine shrinking down to that. And then over here, it goes negative again until I get back to 2 pi. At some point, it's going to cross the axis, and then it's going to connect up with the other one. Okay? So, anybody speak French? Limacon. That's a redneck way of saying it. I mean, this is a C with a little tail, and in France, it's called a limaçon. Limaçon. Anybody speak French? So that's how you say it. Until an actual French speaker tells me otherwise. Say it again? Oh, limaçon. Latin, all those Latin languages. Okay, so this is a limaçon. This would look like a heart. It's called a cardioid. This one looks like it's a 3-leaf flower. And this one, I'm not sure. Maybe this is the one that looks like a heart. Oh, they both look like hearts. These are both cardioids. And what I encourage you to do in your own free time is to just take out your calculators and try them out. I'm sure there are online plotters that would plot these things, so you can also give them a try. So, wow, it's already 1:50. At doing these silly activities, and we don't get to do all the work that we need to do. All right, well, I want to wrap up with a couple of things here. I want to backtrack to parametric equations. And I didn't talk much about the algebra behind this. And you will have homework assignments that will make you think about the algebra behind this. But usually, we're used to graphing functions like y is equal to f of x. For example, y is equal to, give me a function, 2x plus 4. That's a function, right? Going from a function to a parametric function is pretty easy. You would think about this, and what you would do is you would just let one of the variables be equal to t. Usually the independent variable, and if it's y is equal to f of x, x is the independent variable. Sometimes you'll see it as x is a function of y, and then you would want y to equal to t. But in this case, if you let x equal to t, then your y is also going to be a function of t. Y is going to equal to 2t plus 4. And so now these two graphs are exactly the same. Going from parametric to a function might not work so well, especially if these parametric equations don't make, the vertical line test type of function. So it'll be a little bit trickier. But to go from parametric to a function, or to a relationship between x and y, what you would do is you would find a way to combine the equations. And usually, not always, usually you would isolate t in both equations and set them equal to each other. And then when you do that, here t is already by itself. Here t is equal to, let's see, 1/2 y minus 4. And then you would set them equal to each other. You would have x is equal to 1/2 y minus 4. And with enough algebra, you should be able to convince yourself that this is exactly y is equal to 2x plus 4. Okay? So these are ways to use algebra to go back and forth between functions or relations between x and y and parametric equations. And so the first thing we're going to look at next time is the relationship between polar coordinates and parametric equations to see how they're going to work with each other. Okay? All right. That's it for today. Oh, I have due dates now for the assignments. 10.1 and 10.2 are due on Sunday at 11:59 p.m. Okay? Don't wait till Sunday night to work on it. I mean, it's not hard, but don't wait till Sunday night. See you next time.